Infinite series. In simple, we can define infinite series. In fact, we represent it as a capital letter sigma, right? It is the operation of adding an infinite number of terms together. And as we know here, you are adding simply infinitely many number of times, indefinitely. You're adding them. When you add all those terms, that summation will either converge to a limit or diverge to infinity. It means when you add all those terms, there are infinitely many number of terms. When you add them, definitely, the sum may be a finite value or an infinite value. When the sum is a finite value, we say that series is convergent, right? That series is convergent. When the sum is infinity, we'll say that series is simply divergent. Okay. And then how you are getting sum? In fact, that is the basic idea of a series. When you add infinitely many number of terms one after the other, we call it as actually a series, right? For example, if you recall sequence, in sequence what you have, there are infinitely many number of terms, right? For example, if you take 1 by 2 power n as a sequence, right? When you take 1 by 2 power n as a sequence, the first term in the sequence you can identify. Then you can identify the second term, third term, fourth term, like that. You can identify infinitely many number of terms from that sequence. Now, if you add all those terms which are obtained from the sequence, that can be a series. Okay, that can be a series simply. But now anyway, let me take a simple example to understand this conceptually. Okay, and see the example follows like this. Let me take one particular candidate. I'm just naming him as Ravi, and he is training to run a marathon race. Understand? Ravi is training to run a marathon race. I hope you know what is marathon, right? He has to run continuously for a longer distance. All right. Now see here, as part of his practice, he has an unusual training plan. There is a regular plan, but here I'm considering an unusual training plan. What he is doing, you see, on the first day of training, he runs exactly 1 mile. On the first day of training, he runs a mile. But the next day, you see, on day 2, he runs only half of mile. Right? Mile is a kilometer, 2.5 kilometers or so, the regular distance, what you know. On day 1, he's running for only 1 mile. But on next day, he runs half of a mile. And the day after that, on day 3, he runs only 1/4 of a mile. Right? Understand that sequence here. Each subsequent day, he runs half of what he ran the day before. So you can understand on day 4, he runs half of this 1/4 mile, which means 1/8 mile. And on day 5, again half of what he has run on day 4, right? Which means half of 1/8, which is 1/16 mile. So when he continues it like this, you can understand this is an unusual way to train for a marathon. But still, it does illustrate a situation that would require the use of an infinite series, right? And therefore, you see, this chapter, whatever we are going to learn now, it illustrates the use of an infinite series, and it gives certain examples of common series we get in our day-to-day life, and we also see their applications. Now let me extend this example. Totally, to find the distance Ravi ran at the end, what can we do? We need to just add all these distances. On day 1, how much he has run, and on day 2, how much he has run, and day 3, we need to add all these total distances. So what we need to do here, simply we need to add them, right? Like this: 1 mile on day 1, then half mile on day 2, then 1/4 mile on day 3, like this. If you add all these distances, that gives you the total distance he has run, right? But when you look at all those terms, you can notice how each term can be written. See here, each term can be written as 1 divided by a power of 2, right? It is 1 divided by 2 to the power of some n. It is 1 divided by 2 to the power of some n. That's how you see, if n goes from 0 to infinity, then Ravi's training can be represented with this summation notation, right? As n goes from 0 to infinity, this total distance he has run, can be represented as a summation. And that's how, since it has infinitely many number of terms in this sum, we are calling this as a series. And in fact, this series gives you the total distance he ran as part of his training. But let us see how much he has run totally. After 2 days, Ravi has run only 1.5 mile. You see, 1 plus half mile. Day one mile, and on day two, it is half a mile. So after 2 days, totally he has run for only 1.5 miles. Understand, he has half mile left to run before he reaches 2 miles. If you assume 2 miles is his target, after second day he ran for only 1.5 mile. So how much is left to reach the destination of 2 miles? Another half a mile, right? And understand, on day three he run only for 1/4 mile. What it is? It is half of what is actually left. After second day he left actually 1.5 mile, but on day three he has run only half of what is left, correct? And then understand, on day four what happens? He ran only for 1/4 one after day three, when he run for 1/4 mile, how much else is left? Let me just write it. See, let us say the target is totally 2 miles. I'm just assuming it so. On day one he has completed 1 mile. On day one he has completed 1 mile. Then on day two he has completed another half mile. Then on day three he has completed only 1/4. See, after completion of 2 days, you can understand the remaining distance is totally half mile. But still there is a half mile. But still there is a half mile. On day three, he has completed only half of this half mile. You see, half of this remaining half mile, right? When half of this is completed, after completion of 3 days, how much else is left? It is 1/4 mile, 1/4 of total, 1/4 mile totally. But see, on day four, how much he has run? It is only 1/8 mile. This 1/8 mile is again half of what is left, right? It is again half of what is left. So when he complete this 1/8, how much else left again? It is again 1/8. Next, on day 5, he has run only for 1/16 mile, which is again half of what is left here. So like this, what is happening here? You see, this pattern, it will continue, so that he will run half each day of what is left before hitting 2 miles, right? He is just running half of each day what is left before hitting 2 miles. Before reaching 2 miles, whatever is left here, he is running half of this every day. And understand, if he continues like this, even indefinitely, if he continues like this, he will never get completely to 2 miles, because he is running half of what is left, right? He will never reach the 2 mile destination. Every day he runs only half of what is left, right? Whatever is left, he is not finishing that, but he is only finishing half of that. And that's how you can understand, therefore 2 miles is the limit of how far he will run. We cannot certainly calculate how much distance he runs totally, but we can only calculate a limit, right? A target which is 2 miles. That's how, you see, we'll say, since this limit is a finite value here, we'll say this sequence, whatever you have defined here, it is what you call a convergent series, because it is approaching to a finite value here. We'll say it is a convergent series, and the limit, whatever you are getting there, that limit itself is, this summation value. So when you add all these terms, it cannot go beyond 2. It is almost equals to 2, right? So that's how we'll see, we'll generate an infinite series, and we'll also see the sum of all those infinitely many number of terms. Now let me extend this idea mathematically. Let us see mathematically what a series is, and then we'll see how to find mathematically whether that series is convergent or not. See, this is a general idea what I gave you here, but let me just extend this idea mathematically like this. Now let me first define what is series mathematically. Now see, for example, as we discussed, when you are given a sequence of real numbers, let us say un is a sequence of real numbers. If you know the sequence of real numbers, you can clearly write all the terms of that sequence, like, u1, u2, u3. These are all different terms of the sequence. U1 is the first term, u2 is the second term, like this. When you know all these terms individually, you can create an expression of this kind. I mean, you can just add all these terms, first term plus second term, then plus the third term plus third term, and so on. If you continue, sum of all these terms, in fact, that itself is a series, because this sequence has infinitely many number of terms, right? Even this sum is also have what you call infinitely many number of terms, and hence I'm calling it as an infinite series, right? In simple, series is a sum of infinitely many number of terms, and those terms may be obtained from a sequence. That is a different story. But in simple, series is sum of infinitely many number of terms which are obtained from a definite order anyway, right? Then see, we denote it as, like this: summation n is equals to 1 to infinity un, or in simple, we can also write it as only summation un. And particularly, we take un as nth term of the series, right? We take un as nth term of the series. Now see, when we define a sequence, if you recall, when we define a sequence, we had seen when it is convergent. In a similar way, after defining the series, now we need to see when that series is convergent, right? Is every series convergent? Or if it is convergent, in what situation it will be convergent? Now look at it this way. Convergent series. Before getting into the definition directly, let me just add a few points here, and then we can discuss about what you call, this convergence of a series. Now see, when you have a series with you, the series will be like this: u1 plus u2 plus u3, and so on, un. It will have infinitely many number of terms in this, right? When you have such a series, I'm just defining nth partial sum here, right? We have discussed this nth partial sum even while discussing about integration, a similar thing. Nth partial sum. Nth partial sum, see, I'm denoting it as Sn. See what it says: nth partial sum of a series is sum of first n terms in this series. I mean, Sn is equals to, it is u1 plus u2 plus and so on up to un only. Normally in series we'll have infinitely many number of terms, but in nth partial sum, we'll have only finite number of terms. We are just adding only first n terms. I mean, you can understand it like this: if you say S1, it is the first term of the series. Then when you say S2, it is sum of first two terms of the series. Then when it is S3, understand it is sum of first three terms of the series. Like this, you can define different numbers like S1, S2, S3. S1 is the first term, S2 is the sum of first two terms, S3 is the sum of first three terms, and so on. Like this, you can define Sn as sum of first n terms, right? I'm calling this sequence of numbers as sequence of partial sums, right? See, when it is S2, it is a second partial sum, third partial term, and so on. This is nth partial sum, right? When we add different terms in order, we are calling that as a partial sum. And if I take all these numbers together as a set, S1, S2, S3, and so on, Sn, I'm calling this set of numbers as a sequence. And particularly, I'm giving a name to that. It is a sequence of partial sums, right? Now see, where is our question? We are at actually discussing about convergence of a series. Now see, to define convergence of a series, we are first of all defining a sequence of partial sums like this. And understand now, if this sequence of partial sums, Sn, if this is a convergent sequence, then we say the series is also convergent. Understand? After defining the sequence of partial sums, if this sequence of partial sums is convergent, then we say the series is also convergent. If this sequence of partial sums is divergent, then we say the series is also divergent, right? So how to define whether this sequence is convergent or not? we need to take limit n tends to infinity to this sequence Sn. If this limit is a finite value, then we say the sequence Sn is convergent sequence, right? We'll say it converges to this limit L, and when this limit is when this sequence is convergent to L, then we'll say the series summation n is equals to 1 to infinity un is also convergent. And it also, you see, when it is convergent to when it converges to L, we can also say this summation value is also equal to the same L, right? Always whatever the limit you get here, that limit itself is sum of the series, right? So like this, we can define a convergent series. I hope you got the point. To define convergence of the series, we need to take, first of all, sequence of partial sums, right? If that sequence of partial sums, converges to a finite value, then we can say the series is also convergent series. Otherwise, it is a divergent series, right? As we have discussed now, when the sequence of partial sums converges to a finite value, it is okay. Otherwise, we can say the sequence is divergent, and obviously the series is also divergent. And when series is divergent, the sequence may be either infinity. I mean, sequence may approach to infinity or minus infinity. When the sequence approaches to plus infinity or minus infinity, accordingly, even the series also diverges to plus infinity or minus infinity. Right. Now let's take an example. Look at this example carefully. 1 plus 1 by 2 plus 1 by 2 square and so on, 1 by 2 power n and so on. Now let us see whether this series is convergent or not. Right, to identify whether this series is convergent or not, we need to take nth partial sum of the series. That's where we are, we are discussing, right? We need to define a sequence of partial sums. If that sequence is convergent, accordingly, we can discuss about convergence of a series also. Before that, you can understand this is clearly a geometric series. I hope you remember that it is, it is in yellow color here. You can see 1 plus x square and so on. Such a geometric series it is. Anyway, keep that in mind. Now I'm just trying to take the nth partial sum of this series. What is nth partial sum? To get the nth partial sum, we need to take sum of first n terms here, right? So the first term is this. Understand the first term in the series is 1, right? It starts with 0. So first term is this, and then you see, if you continue like this, 1 plus 1 by 2 plus 1 by 2 square and so on, 1 by 2 to the power of n. So I'm just taking sum of first n terms like this, Sn. I need to calculate sum of these terms. Once if I know the sum of these terms, then I can take a limit to that, and then I can see whether that is a sequence, whether that is a convergent sequence or not. Right? As you can see here, when you add sum of first n terms like this, 1 plus x square and so on, x power n, it can be written as 1 minus x power n plus 1 by 1 minus x when mod x is less than 1. Right? When mod x is less than 1, some of these terms can be written like this. Now I'm just trying to use this simple idea to write the sum of these n terms. Right? If you just compare these two, you can see x is equals to 1 by 2. I mean, the common ratio is 1 by 2 here. And as we know, modulus of 1 by 2 is clearly less than 1. We can proceed by this particular formula. Right? So if you just substitute x is equal to 1 by 2 in this, see how much you'll get. So then the series, I mean the sum of n terms Sn is equals to how much you'll get, I'm just substituting x is equals to 1 by 2. So 1 minus 1 by 2 to the power of n plus 1 divided by here also 1 minus 1 by 2. Then it is equals to, see how much you'll get, 1 minus, look at the denominator first. When it is 1 minus 1 by 2, we can write it as simply 1 by 2 only. And in the numerator also, how can you write this? You see, 1 power n plus 1 is anyway 1 only, and in the denominator it is 2 power n plus 1, right, for this term. Now see, when you have 1 by 1 by 2 here, something by 1 by 2, you can take this 2 to the numerator, right? That's how we'll get it like this, 2 times, these things I'm writing them as it is, 1 minus 1 by 2 to the power of n plus 1. The same thing I've written here, you see, you can just understand with a simple calculation. So when you add all these terms based on this particular formula, you will get Sn as this much. Now see, this gives you nth term in the sequence of partial sums, right? Sn is given by now this sequence, right? This nth term. Now see, for that particular sequence, I'm just calculating the limit n tends to infinity. From that, you will see whether it is convergent or not. Now, when you take limit n tends to infinity Sn, as you see, I'm just substituting, you see, Sn is equal to all these things. When I substituted that, what happened to this, you see, as n approaches to infinity, it is clear, you know, 1 remains as it is anywhere. But when you look at the denominator in the second term here, as n approaches to infinity, even this 2 to the power of n plus 1 also approaches to infinity only, right? As n approaches to infinity, even this 2 to the power of n plus 1 goes to infinity, definitely. And therefore, this goes to, you know, 1 by infinity, right? That's how it goes to 0. And therefore, you know, you will get the limit as simply 2. When the limit is 2, you can understand it is a finite value, and therefore you can say the sequence of partial sums Sn is a convergent sequence. Right here, Sn is a convergent sequence. When the sequence Sn is convergent, automatically you can say the series is also convergent only. Right? Since the sequence Sn is convergent, you can say the series is also a convergent series. Right? And to where it converges, to the same limit whatever you got there, it converges to 2 only. And therefore, you see, you can write this series, you know, sum of all these terms is also equal to the limit what you got here, 2. Right? That's how you see the same example what we discussed earlier, the marathon example. The same thing, you know, I have just calculated it as, mathematically I have calculated it here. Earlier, you know, we have just discussed it with a real things. But now when you solve the same thing mathematically, still we got the same thing, you know, the limit as 2, right? The same thing, you know, we can just identify like this, whether a given series is convergent or not. Right? If anybody have any questions in this, you can. I just remove this one. I don't know how you got this. Oh, something went wrong. Okay. So the limit doesn't exist here. Anybody have any questions? I'm just allowing you. Yeah. If you have any questions in this, you can. All right. Let's see these two examples one after the other. Look at the first one. What you have there, you see 1 minus 1 by 3 plus 1 by 3 square and so on. We need to see whether that series is convergent or not. Right? See, as we know, to identify whether a given series is convergent or not, we need to take what you call nth partial sum, right? So if I define the sum of first n terms, Sn, see how much you'll get here. It is 1 minus 1 by 3 plus 1 by 3 square minus 1 by 3 cube and so on, will take up to minus 1 to the power of, because you see here also, n is starting from 0. Look at it. Right? I mean, n is starting from 0. That's how, to get nth term, I'm taking this as minus 1 to the power of n minus 1 into 1 by 3 to the power of n minus 1. So these are the first n terms, and I'm taking only the sum of first n terms in this series. Okay. Now see, when it is just like this, I cannot directly add all these things, you know. So for my convenience, I'm rewriting them like this. See how I am rewriting. Sn is equals to 1. I'm writing it like this, you see, plus minus 1 by 3. Then here also plus, because you have a square here, I can write it as minus 1 by 3 whole square. So when you have a square, even if you have a minus sign here, it doesn't matter, because you know minus square is plus only. And here also you see plus minus 1 by 3 whole cube. This can be written quite easily, right? And so on. Here also, I'm just writing it like this, you see, minus 1 by 3 whole to the power of n minus 1. We can write quite easily, we can write like this, right? So now if you observe this, clearly it is a geometric series with the common ratio minus 1 by 3. Right? The common ratio here is minus 1 by 3. And if you recall the formula, what it is, 1 plus x square plus and so on. If it ends with x power n minus 1, and if mod x minus mod x is clearly less than 1, right? When it is mod x less than 1, we'll get this as how much you'll get here? See, 1 minus x to the power of n divided by 1 minus x. Now see, when you add all these terms, we'll get the series as this when mod x is less than 1. Clearly, here x is minus 1 by 3, when you take mod x, it is modulus of minus 1 by 3. Though it is negative when we are taking modulus, definitely it is less than 1 only, right? Then you see, since mod x is less than 1, we can proceed by this formula. And therefore, you can see Sn is equals to, we'll get it like this. You see, 1 minus, in place of x, now I am substituting minus 1 by 3. So minus 1 by 3 whole to the power of n divided by 1 minus of minus 1 by 3, So it becomes 1 plus 1 by 3. And therefore, we'll get it like this. What it is 1 plus 1 by 3 means 4 by 3 in the denominator. So when it is 4 by 3, I can take that to the numerator. So we'll get it as 3 by 4 multiplied by 1 minus, I'm just writing it like this, you see, minus 1 to the power of n divided by 3 to the power of n. I'm just separating that. I'm just separating that into the numerator as well as the denominator. So this can be done, right? So how I got this 3 by 4 here? Because in the denominator here, you are getting it as 4 by 3. So something by 4 by 3 is there, you can take 4 by 3 to the numerator. That's how I got it as 3 by 4. Now, see, this is Sn. Now, to identify whether that sequence is convergent or not, I'm taking what you call the limit n tends to infinity Sn. So for this, how much you'll get the limit, you see? This is equals to 3 by 4. Let me just write all this. Limit n tends to infinity. Three by 4 times, how much you'll get? I'm writing anyway all these things. 1 minus 1 to the power of n divided by 3 to the power of n. Right. One thing is for sure here, what happens? When n approaches to infinity, certainly minus 1 to the power of n gives you either plus 1 or minus 1. Nothing other than that. That's how you can understand whether it is minus 1 or plus 1, it is a finite value. Right? Clearly, as n approaches to infinity, minus 1 to the power of n here, the numerator, gives you a finite value. Then come to the denominator. When it is 3 power n, when n approaches to infinity, certainly this 3 power n approaches to infinity only. So when it is this, finite value divided by infinity value, certainly, this approaches to 0. And what you have here is 1 minus 0. So totally within the bracket, as n approaches to infinity, we'll get this as simply 1 only. And therefore, the limit here is 3 by 4 into 1 now. It is 3 by 4. Understand? The sequence is approaching to a finite value 3 by 4. That's how you can say the series is also convergent. Therefore, summation, see, I'm writing it like this. Therefore, summation n is equals to 0 to infinity minus 1 to the power of n into 1 by 3 to the power of n. Because see, I'm starting with 0, I can write this. Summation n is equal to 0 to infinity minus 1 to the power of n into 3 by 3 power n is also convergent. Right? From here, when the limit is 3 by 4, you can say the sequence of partial sums is convergent. When that sequence of partial sums is convergent, then you can say even this is also convergent. Right? And moreover, you see, when it is convergent to this 3 by 4, you can also say this summation. What is this? Summation minus 1 power n 3 by 1 by 3 power n. Even this summation value is also equal to 3 by 4. Right? Like that, you can test whether a given sequence, whether a given series is convergent or not. Now, let me just continue this problem and then I'll allow you. Then see how much you'll get here. Look at this. See, first of all, don't misunderstand the question. Look at all the terms in the denominator. They are like this. 1 divided by, they are not decimal points, but they are like this. 1 into 2. plus 1 by 2 into 3, they are all in product, plus 1 divided by 3 into 4, and so on. If you continue like this, you see what you are getting. In the first term you have 1 into 2, in the second term you have 2 into 3, then in the third term you have 3 into 4, and so on. If you continue like this, in the nth term you will get n into n plus 1, and so on. This is the series. So if you write the sequence of partial sums, I mean nth partial sum Sn, you will get it like this. You see 1 divided by 1 into 2 plus 1 divided by 2 into 3, 1 divided by 3 into 4, and so on. The nth term, it is 1 divided by n into n plus 1. So this is the nth partial sum what you can consider. But see, if it is like this, how can we add them? When it was a geometric series, somehow we can do it. When it is only sum of first n terms like this, 1 by 1 plus 2 plus 3 plus and so on n, we can write. So sum of first n natural numbers is this. We have some standard formulae. But when you have a series of this kind, right, looks like little difficult, but we have an idea like this. What you can do here is, look at the nth term first of all, nth term of this series, which is 1 by n into n plus 1. Correct? Recall partial fractions. When you have these kind of expressions, we can something write like this. You see, a by n plus b by n plus 1. Linear expressions, both n and n plus 1. So if you calculate similar to a by x plus b by x plus 1, if you calculate a and b values, you will get them like this: 1 by n minus 1 by n plus 1. Right? See, this product 1 by n into n plus 1 can be written as 1 by n minus 1 by n plus 1. Clearly, you can take LCM and check it. So keeping this idea in mind, I'm just trying to rewrite all these terms. So you can understand when it is 1 by 1 into 2, I mean, you can take n is equal to 1, you see. Keeping this idea in mind, I can rewrite this product as 1 by 1 minus 1 by 2. Plus, similarly in the second term, when it is 1 by 2 into 3, you can take n is equal to 2, right? So we can write it as 1 by 2 minus 1 by 3. Then similarly in the third term, we can write it as 1 by 3 minus 1 by 4. And so on. If you just extend this, the last term can be written as 1 by n minus 1 by n plus 1. Right? So sum of first n terms, nth partial sum can be written like this now. If you look at these terms, clearly in the first term, the second one is minus 1 by 2. And this can be cancelled with the first term in the next term. 1 by 2 minus 1 by 2 can be cancelled out. Similarly, here also you see minus 1 by 3 plus 1 by 3 can be cancelled out. And see, obviously, though we have not written that, this minus 1 by 4 and the next term will have definitely 1 by 4, and that those two can be cancelled out. So like this, if you cancel all the terms, even you can cancel this 1 by 4 with the previous term, with minus 1 by n. Certainly it will be there, minus 1 by n, and that can also be cancelled. So if you cancel all these terms 1 by 1, what remains here, you see, this first term and the last term, except these two, remaining all will be cancelled out. And that's how you see, if you write Sn, we'll get it as 1 minus 1 by n plus 1. So this is now, you see, Sn. Now this is the sum of first n terms of this series. Now let me take, limit n tends to infinity to this nth term or this sequence. So therefore, limit n tends to infinity, Sn is equals to limit n tends to infinity 1 minus 1 by n plus 1. So if you take n tends to infinity to this, as we know, n plus 1 approaches to infinity, and therefore 1 by n plus 1 approaches to 0 directly, and therefore we'll get the limit as 1. When again the limit is a finite value, you can say Sn converges to L. I mean the sequence of partial sums converges to this number 1. When the sequence of partial sum converges, therefore automatically the series summation un is all this series, it also converges to the same limit 1, right? To wherever the sequence is converging to the same limit, even the series converges. And therefore you can see now sum of all these terms is exactly, not exactly of course, it is almost equal to 1. So like this, you can test the convergence of a given series by taking nth partial sum, I mean sequence of partial sums. Now, look at these two statements. I can say general properties of some series. See, when you are given an infinite series, the convergence or divergence of that infinite series unaffected, it remains unaffected even after addition or removal of a finite number of terms. If you add or remove some finite number of terms from the series, it really have no influence on the convergence or divergence of the series. If it was convergent earlier, even after addition or removal of the terms, still it remains as convergent only, right? If it was divergent, it remains as divergent only, right? In a similar way, when you are given an infinite series, the convergence or divergence of that series remains unaffected, even if you multiply every term by a non-zero number, right? Even after multiplication by a non-zero number, if it was convergent earlier, even after multiplication, it remains as convergent only. Of course, the limit may be different after taking multiplication by a non-zero number to where the series convergent may be different. The sum of the values may be different, but the nature of the series remains same. I mean, if it was convergent earlier, it remains as convergent even after taking product, even after taking multiplication. So keeping all these things in mind, you can just have one simple idea. You see, when you are given an infinite series, there are exactly, I can say, two different types of series now. A series with positive terms. You know, when you define a series, it will be something like this: u1 plus u2 plus u3 and so on. This series may have all positive terms. Every term in the series is positive. If not this, you may have an alternating series. Like, you know, alternately we have plus minus u1, then minus u2, then plus u3, then minus u4, and so on. Right? Now see, when you are given series of this kind, we need to see the convergence of those series. Understand, there is one more idea. What if every term in the series is negative? If every term in the series is also negative, we'll take minus common from them, and we just will understand it by taking, you know, the idea of series of positive terms, right? So that's how we won't discuss series of negative terms especially, but we only consider series of positive terms or series with alternate terms, right? So in these two cases, we need to see the convergence of the series.